So we looked at the example of an exponential distribution where we first take the log of the joint likelihood. So we take the joint likelihood independent observation, so we can take the product. If we take the log, it becomes a sum of logs. That's easier to work with. Then we could simplify the function a little bit, and then we could take the derivative in order to find that point where the slope is 0, and that should be a maximum or a minimum of the function, and we are looking at that point where the likelihood is maximized. That point where if we take those parameters, it is most likely to observe the data that we did indeed observe. Now the exponential distribution is a relatively straightforward distribution, a bit easier to show how to work out the derivative. Let's now look at an example that is a bit more relevant, namely the linear model. So we already know that for a linear model it's best to use OLS, and this doesn't change. But one could, in principle, use maximum likelihood to estimate the parameters of the linear model. And so in the next few slides we look at how that would work out. So at the beginning here we have the specification of the linear model that you are familiar with. So we have a dependent variable y, we have a linear relationship between x and the parameters, x times beta, and then we have a normally distributed error term that is distributed around 0 and that has a particular variance. So we have two parameters to estimate, the slope parameter is beta and the variance of the error term, sigma squared. And because we say that this is a normal distribution, a different way to formulate this would be to say that y has a normal distribution around x times beta as its mean and with a variance sigma squared. And the normal distribution has a particular equation that we saw much earlier in the class, and which is on this slide. So this 1 over the square root of 2 pi times sigma squared times the exponent of the residual squared divided by 2 sigma squared. That is the probability density function for a normal distribution if we assume that y distributes around x beta. So if you see this as a function where y changes given a particular value of beta and sigma squared, we have a probability density function. If you look at this function for different values of beta or for different values of sigma squared, then we have a likelihood function. So we start again by first of all assuming independent observations, assuming that different observations, say different respondents in the survey or different countries on which we collect data, do not influence each other. So if we assume these independent observations, then the overall probability density function for the entire sample becomes the product of the probability density function for each individual observation. And then we take the log, because we tend to look at the log likelihood function. So this product of each independent observations becomes the sum of the log of each of these independent observations. Now we're going to focus a little bit on this first part of that equation and see how we can simplify that. We want to express this function a little bit more comprehensible so that we can calculate derivatives and so forth. So here we look at this first part. If you take the log, it simplifies as follows, as on this slide. And that means that the same equation can be reformulated as here below. So we have minus n over 2 times the log of sigma squared, minus n times 2 of the log of 2 pi, and minus 1 over 2 sigma squared times, and then this matrix algebra there, and you might recognize that y minus x beta is the residual, and so residual means this is the sum of squared residuals. So this last term, the part that has the matrix algebra, is a way of, in matrix algebra, of saying the sum of squared residuals. So you will see that the first item is a function of sigma squared, the second item does not have either of the two parameters, and the third part of this equation has both sigma squared and beta. So we want to optimize with respect to two separate parameters, sigma squared and beta. Let's first focus on sigma squared. So we take the derivative of this function towards sigma squared. You will remember that the second part of the equation did not have sigma squared in it, so it's basically the sum of the derivative of the first part towards sigma squared and the derivative of the last part towards sigma squared, which is worked out here and then simplified. And then when we equate that function to 0, we can work out for which value of sigma squared the derivative is 0, and therefore for which value we have the maximum on this likelihood function. So in this case, the likelihood function is relatively straightforward. It's like a parabolic function that has this shape. So if the derivative is 0, we know that we have the maximum point. For more complicated likelihood functions, you would have to show that this is actually the maximum. But here it's relatively straightforward. So if we find that one point where the derivative is 0, we know that we have a maximum. We know that we have that value for the parameter where observing this particular data is most likely. And that value, in this case, our maximum likelihood estimate for sigma squared is 1 over n times the sums of squares residuals. So that is the maximum likelihood estimate for sigma squared. An interesting question is how that actually relates then to the OLS estimate. So you might remember from a while back that the OLS estimate of the variance of the residuals is E prime E, the sum of squared residuals, over n minus 1. The maximum likelihood estimate is E prime E over n. So it's slightly different. We already know that the OLS estimates are unbiased. So that means that the maximum likelihood estimate, which is slightly different, is in fact biased. So this is a biased estimate of the error variance. But you will also see that because this minus 1 is of course relatively small, if you have a small sample size, it makes quite a difference whether you divide by, say, 10 or 9. But if you have a large sample size, say 1,000,000 observations, it doesn't matter whether you divide by 1,000,000 or 1 less. So as the sample size increases, this bias disappears. And therefore this is a biased but nevertheless consistent estimator of sigma squared. As the sample size goes to infinity, the bias disappears. And this happens to be very common for maximum likelihood estimates. They are quite often biased, but consistent. Now when we take the derivative towards beta instead of towards sigma squared, we will see that this E prime E, this sums of squares residuals, is really key to estimating beta. The bottom line is, if you find the value of beta that minimizes E prime E, you have found the value for beta that minimizes the maximum likelihood function. Maximizes, apologies. So if you find the value that minimizes E prime E, you find the value that maximizes the likelihood function. And you will also maybe remember that the OLS estimate is defined as that estimate that minimizes E prime E, the sums of squared residuals. In other words, the maximum likelihood estimate for the betas for the linear model are the OLS estimates for beta for the linear model. So we don't have to do the derivation here because we have that on earlier slides. They are identical. So a maximum likelihood estimate of the linear model will give the same beta values, but it will give a slightly biased but consistent estimate of the sample variance, of the error variance.